Thanks for coming to Creative Coding with Compose, the next chapter. So let's get started. So before we begin, a little bit about me. My name is Tasha, and this is my cat, Spooky. Quick shout out to her, because she helped a lot with the slides by sitting on my keyboard and staring right in my face. So, yep, if this presentation turns out good, it's because of her. So when I'm not helping people find matches working at Tinder, I like to play around with some creative coding and generative art in my spare time. And so this is what the talk will be about. So let's begin by unpacking those terms, creative coding and generative art. When we think of code and art, they seem fundamentally opposed. Code is logical, structured, and ordered. And art, on the other hand, is expressive, it's unpredictable, and in a sense, it's like order versus chaos. But very interesting things happen when these two worlds collide. So this is what we'll be taking a look at. And when we ask the question, well, where do these worlds collide? That's where creative coding comes in. Creative coding is a way of creating something that is expressive rather than functional. So you're coding with the goal of not creating an app or a specific piece of functionality. You're kind of coding in a way where creativity and curiosity are your guiding principles. A subset of creative coding is generative art. And here we use a mixture of algorithms, randomness, and other interesting tools to create something aesthetically pleasing and sometimes unpredictable. And the beauty of it is that you create the rules and the algorithms in code, but with the introduction of randomness and other things, you never know exactly what you're going to get. Creative coding concepts are applicable in a lot of different fields, and they pop up quite frequently. For example, the first area that we can talk about is exploration. So you, as the coder, or in this case, the artist, can use creative coding as a vehicle, a new fun way to learn and understand graphics APIs and mathematical concepts. It allows you to kind of break free from the conventional approaches of coding and get immersed in a more experimental setting. And the second aspect is data visualization. So data visualization is a huge area that incorporates a lot of concepts of creative coding, where it's vital to be able to intuitively understand large, raw data sets. And lastly, and this one's a bit of a blanket or umbrella statement, concepts in creative coding and generative art can have a tendency to enhance UX or enhance the way a certain piece of UI feels. For example, an app could use a generative art algorithm to create unique avatars for users, or to create a really fancy loading animation. And of course, concepts like involved in creative coding are applicable to the world of gaming as well. So the motivation for this talk is an event that took place earlier this year in January, called January, and it was an artificially generated month of generative art. There was a new prompt for every day of January on the January website, and folks were encouraged to create pieces of generative art using whatever tools or frameworks they were most comfortable with. Here are a few examples of what other people have created using a lot of different tools. A lot of people use JavaScript or this other framework called processing. And I, of course, being an Android engineer, familiar with Compose, wanted to try to use Compose to create generative art pieces for January. These are a few of the things I ended up creating during that month. And I found this entire process to be very fulfilling, and it completely changed my relationship with coding. I no longer completely saw coding as a utility to create functional things, and instead saw it as something more. So in this talk, I want to share with you some of the approaches that were involved in creating works like these, pieces like these, and use them as a vehicle to explore some concepts around drawing APIs and other cool things in the Compose world. So Saul Lewitt was a conceptual artist, and he once said that the idea becomes a machine that makes the art. For us, this is true. Since we're going to be using Compose, we'd want to say that the idea becomes a composable that makes the art. So in this talk, we'll go through this creative process split up into 3 phases. The first phase being form, and here we'll start by drawing forms and shapes. Then we'll move on to the generating phase, where we'll create variations of those basic forms. And then lastly, we'll look at how to apply some finishing touches to our pieces. And along the way, we'll explore the drawing APIs and concepts necessary to achieve these. So let's start with form. First, let's take a quick tour of the composed canvas and see how we can start drawing our forms. The canvas composable allows us to draw things within a draw scope, which provides a declarative and stateless API to draw onto. In the canvas, our coordinate system is going to look like this, where we have our origin at the top left, and the bottom right is going to be as big as the width and height of the container. And draw scope exposes a parameter called center, and if we were to draw our circle there, we'd be placing it at halfway between the width and the height of the container. With that out of the way, let's kind of prime our canvas a bit just as an artist would. So you can give your canvas a specific aspect ratio. I tend to prefer something like this, halfway between a 1:1 and the device aspect ratio. I also like adding a specific background color to the canvas before I start drawing things on it. I tend to prefer some of these warm tones, like this eggshell type tone, and it kind of makes it look like old parchment, and it really makes the colors pop. We have our canvas ready, so now let's move on to taking a quick tour of the drawing APIs. So some of the basic ones that you might already know about are draw circle, and this takes in a color, a radius, and a center. And the center is defined as an offset, and an offset, as you might know, is basically a data class that represents an XY coordinate. Next up, we have draw line. Draw line is interesting. It takes in a start and an end offset to define your start and end points for the line, and it also takes in the width of the line as a parameter. And lastly, you might be familiar with the draw rect function, which takes in a top left coordinate and then takes in the size and then figures out the rest of the rectangle for you. So there are other drawing APIs like draw oval, draw rounded rect that you can kind of use and do fun stuff with. But today I want to take a look at how to break away from some of these forms and try to create something a bit more intricate, like various polygons. So how would we approach drawing these in a way that's not super complicated? So one of the ways to draw or envision polygons like these is to imagine them inside a circle and then think about their vertices as touching the circumference of the circle. Once we know what those points are on the circle, we can just connect the dots. How do we find the points? That's where trigonometry comes in, yay. And how do we connect the dots? That's where our path object comes in. So let's take a look at all the trick stuff. So if you love geometry and math like me, no. Here's a quick tour of polar coordinates and radians. So if you recall from high school, college, I don't know, the full rotation of a circle, of a unit circle, is 2 pi radians. And if you know the radius of the circle, and if you know the center, you can find any point along the circumference of the circle for a given angle, using sine and cosine for the x and y coordinates. So using that, we can kind of chart the points of the polygon we want to draw on the circumference of the circle. All right, so with that in mind, let's see if we can define a more general draw polygon function, just as how we saw draw line, draw rect, and draw circle. We can start by defining some basic parameters. Obviously, we'll need a center to define the center point for the shape. We'll need the vertices as a parameter, so we can kind of change the kind of shape we're drawing. We'll need the radius, which determines the size, and a path object, and this is optional. If you want to reuse path objects across drawing calls, you can pass it in, reset it, and then keep drawing. And of course, we'll pass in a color, and another interesting parameter, rotation, which will determine the initial orientation of the shape. So let's expand this function and see how we'll implement it. So first up, like we said earlier, we need to find the points along the circumference for the shape. So we'll first start by calculating the increment angle for each vertex. So like we said, a full circle has 2 pi radians. We divide that by the number of vertices, and now the angle decides how much we have to turn for each new line we draw in our polygon. Now our starting angle is defined by the rotation parameter we pass in, and we subtract half pi. This might seem a little mysterious, but the reason we do this is because we want to start drawing at the very top of the shape. A unit circle the 0 radian point is on the right side. So this subtraction basically rotates the drawing pen counterclockwise by 90 degrees. So next, within the for loop, we loop through each vertex, and we find the angle with which we need to turn the pen by. And this is where the sine and cosine come in to give us the actual x and y coordinates of these points. Once we chart our points out, all we need to do is join them using the path. And here, if it's the first vertex, we just move our pen there. But if it's any of the other vertices, we just draw lines and connect the dots. Finally, we will close the path and draw it. One cool thing about representing shapes this way is that you can just vary the number of vertices and quickly get pretty much every polygon out there. So if you set it to 3, you'll get a triangle, obviously. Set it to 5, you get a pentagon. And if you change the rotation parameter, you're going to see some interesting things that you can do as well. So just varying the rotation parameter that you provide as radians, you can rotate your shape. Here's the triangle rotated by pi, or 180, and here's the pentagon rotated by 90 degrees, or pi by 2 radians. Okay, so we have our shapes. What do we do with them? So now it's time to enter the generate phase. We've got the mat down to generate some of these, and now let's see how we can achieve some variations. So the very first thing we can start to do is identify some levers that we can change of the shape. And let's start with the first 3 most important things. First one being repetition. Just draw a bunch of them. Second thing being alpha, and the third thing being size. And just by varying these, you can already start to see some interesting patterns form. For example, here, we're going to make the shape of the size change with every shape we draw. And we also specify a smaller alpha value, like 0.4, and that really allows the colors and the shapes, the repeated shapes, to blend. But we can do more, and this is where we get into the fun stuff. Let's try varying colors and vertices. So you might define a palette of colors for yourself, for example, and every shape you draw, you can pick a color from that palette and use that to draw your shape with. And you can also vary the number of vertices, and you can get shapes with increasing amount of sides, and the combination of the two can start to yield some interesting patterns. So you can keep messing around with these, because these in and of itself can be interesting, or you can do even more. Let's just start shifting them up. So here we're going to alter the vertical offset of the shapes with every iteration. And the y offset parameter here is going to be tied to the number of iterations that you're running. And if you do this, you'll start to see like slight shifts every time you draw the shape, and you're starting to get something that's a little more dynamic than just a bunch of shapes on the screen. Now, just by varying the y offset a little bit more, instead of 0.2, just using 0.5 as a factor to vary it by, you can see something that looks way different than what it was before. And that's where the beauty of this thing lie, where you can change small things, make small tweaks, and get some very interesting results. Speaking of interesting results, let's go a little crazy and let's start changing the rotation of our shape. So here we're doing 2 new things. The first thing is the radius of the shape, or the size of the shape, is now a function of the ratio, or the iterations you're running, squared. So you're going to get not the shape changing very uniformly every iteration, the shape's going to change a little differently every iteration. Also, we change the rotation. And here we're saying that if we're drawing an even iteration of a shape, then we'll rotate it by 180, else we'll leave it where it is. So these are all kind of values that we've hard-coded, and we're kind of just moving them around and seeing what we can do with it. But the real generative part of this comes in when we introduce some randomness. So let's take a look at what happens if we did 2 more things. Shuffle our colors and add a bit of randomness to the y offset. Now, if you do this repeatedly in combination with the other things you've been changing, you'll start to see patterns and forms develop that you couldn't perceive or think about manually. And that's because of the randomness, which is introducing patterns that you can really think about. And in this case, sometimes you might see things that are not very appealing or don't look like very much, but every now and then you'll see something that's super cool. All right, so we're tweaking, we have all these things that we're changing, and there's so many things that you can change, so many more things you can change, and all of this can get a bit overwhelming. So one of the ways that I like to kind of organize all this is to just create like a control panel where I can start tweaking these things, and it basically turns into this little app where I can tweak all these little parameters. So for example here, we'll just say, oh, well, these two arrows change the alpha of the shape. And let's have some more. These two buttons now change the number of shapes that you're generating. So if you keep adding more, you're going to see some very interesting optical effects as well, as the alphas and the colors blend with the increasing number of shapes. And you can randomize the colors and change the number of vertices. So you can imagine that there's so many permutations, combinations of all these factors, and it could start to create variations, generations, and essentially little pieces of art, you might say. And if you introduce randomness into this, well, then that's getting awesome. So far we've been drawing shapes at a time, a few shapes at a time maybe, but what if we wanted to do something a bit more dynamic and sort of think about, splashing paint on canvas over and over again and drawing in layers? If we do something like this, where we're drawing maybe like 50 or hundreds of dots and rects and circles on the canvas, we kind of had to keep track of the state. And that could get unwieldy very quickly. So maybe there's a way to kind of reason about this and say well, would there be a way to draw in layers or make our canvas stateful? Why do we need to make our canvas stateful? Well, because it is not stateful by default. Remember from earlier, the draw scope of the canvas is stateless, which means that if you try to draw a bunch of things and try to draw a bunch of things again, it's going to erase what it had before. So you can't cumulatively draw or record your drawings on the canvas. But let's look at one of the ways in which we can achieve this stateful canvas idea, where we can keep drawing and have our canvas build up a memory so that it doesn't overwrite the previous draw commands. One way to do this is to redirect all your drawing calls to an image bitmap and then put that image bitmap into your canvas. So instead of drawing on the main canvas, you're redirecting it and indirectly putting the image bitmap with all your draw commands on the canvas. So let's expand upon this and see what else this would entail. So here we can use the draw with cache modifier because it comes in handy to set up a few things and cache a few things before you draw your actual thing. So in your draw with cache block, you can do all that setup and initialization, and then as we'll see later, there's another function that you can call to actually perform the drawing. So to actually do this redirection of the draw commands, we'll first need to set up a separate image bitmap, and we'll actually need to set up a secondary canvas to draw the stuff onto. So these three things in tandem will allow us to draw or to redirect our drawing commands to this image bitmap. The draw scope is what we'll need to actually call the draw command. So once we have our bitmap, the canvas that wraps the bitmap, we can use that draw scope that is associated with the same thing to draw our shapes. And in this lambda of the draw function of the draw scope is where we will put all our draw commands. And then lastly, we need to actually take that image bitmap and apply it onto the main canvas, and that's where we call onDrawBehind, which will take the whole image bitmap and whatever's going into it, and then put it on the main canvas. So you could wrap all of this up and create a utility composable for yourself. You can call it whatever you want. I'm calling it stateful canvas. And here I'm just using a box because it's just a lightweight dumb composable, and I can use the draw with cache modifier right in the box. And inside the draw with cache modifier is where all the brains of this operation goes. So with that, we're essentially getting this stateful canvas effect or stateful canvas idea where we're redirecting all our draw calls we're not drawing on the main canvas. All right, so how would you actually use this in practice? So this is an example where we're taking essentially a bunch of dots and splashing them onto the screen. And every time you click this add button, we're going to say, well, splash 100 more dots on the screen, splash 100 more dots on the screen with a different color. So it's almost akin to throwing water balloons full of paint on a physical canvas. And what the stateful canvas is giving us essentially is that every time we change the number of blobs or the color of the blobs that we want to draw, and we go through that repetition, we don't overwrite our previous draw calls. So we can build this up layer by layer. And in doing so, we can experiment with another cool parameter. Well, here's the thing about the add click. So the other thing that we could try to do is experiment with the blend mode. Because we're drawing layer by layer, we have a lot of things overlapping each other. Using the blend mode can yield some interesting results. Here we're using the XOR blend mode, which will essentially create transparency in areas where the two things overlap. So if you can imagine, as we draw a bunch of blobs on the screen and we draw more blobs over them in different colors, the areas where the blobs overlap end up looking transparent, and we can start getting some cool looking patterns. Okay, so we took a whirlwind tour through generating things. Now let's look at how to process and transform them and apply some final touches. So when I was working through this, I kind of felt that all these shapes were looking rather flat and bland and artificial, and after all, they're made with code, so why shouldn't they? But could we process these images somehow through code to create something that looks a little more natural? And this is where I wanted to see if we could add texture to the pieces to make them look a little less artificial and a bit more natural. Could we simulate the effect of ink on paper, for example, and create this noisy, grainy effect? And I use the word noise intentionally because it turns out that noise functions are really good at creating grainy, sandpapery textures, or any natural texture. So let's take a look at what noise functions actually are. Noise functions are large, complex algorithms that I could possibly not go into in this talk, but suffice to say, they produce this coherent randomness, or this smoothened randomness, kind of like TV static, if you can think about that. And with noise functions, every value that you get at any given input is similar to the surrounding value. So that's why you kind of see this uniformity, even though it looks a little messy. And noise functions are used a lot in generative art, in graphics processing, gaming, CGI, to create or simulate clouds, textures, terrain, things like that. For our purposes, we're going to see if we can somehow superimpose a bunch of noise onto our piece. Let's see if that's coming out okay. And see if we can achieve some texturing on the piece, some graininess. And turns out we're going to have to talk about shaders, because shaders are very powerful, and one of the things they can do quite well is generate noise. Let's take a brief anatomy tour through a basic or typical shader. I'm not going to go into too much detail here because it can be a talk in and of itself. In fact, there is a talk on shaders, so definitely check that out. And instead, we're just going to walk through the anatomy really quickly and then look at how to use it for our very specific purpose. So the first thing to note is that shaders run on every pixel, and it allows us to define the color for every pixel that it runs on. Now, this is what a shader looks like. And this is written in AGSL, or Android Graphics Shading Language, which is similar to other shading languages out there. And this is what you would use if you were trying to use a shader in Android. So to start with, these are the uniforms. And uniforms are essentially pieces of data that you can pass in from outside the shader, and they remain constant no matter how many times the shader is executed. So think of this as a way to pass in application data or application state into your shader. Next up, we have the inputs and the outputs of the shader. So the main function of a shader is the main function, and this is what will run when a shader is executed. And the input of the function is essentially a two-dimensional vector, which is a coordinate of the pixel that it's running on. And the output is a four-dimensional RGBA vector, which represents the color of that pixel. And here, note that because In the red channel, we are using the x coordinate, and in the y channel, we're using the Greek coordinate. The red color will increase from left to right, and the green color will increase from top to bottom. So now with this kind of very brief anatomy, let's take a look at how to actually use this for a very specific purpose of applying noise to a composable. So the high-level picture would be, we need to somehow get the contents of our composable into the shader, apply noise to it, and essentially color each pixel with the noise value, if the noise is applied there. So how would we go about doing this? So let's expand this part a bit more. So first up, we'll create the noise. Second step, we'll get the color of the input composable, or the image that we're trying to shade, at that coordinate that the shader is running on. And then finally, we'll just mix the noise with that color and output the final color. And here, we're going to introduce a new uniform called image. And the image uniform is going to represent the contents of our composable as a shader. And that's what's going to allow us to get at the colors or the pixels of the thing that we're trying to shade or process. The other uniform we're going to introduce, or we optionally could introduce, is an intensity uniform, which allows us to change the intensity of the noise from outside the shader. All right, so let's dig a little deeper. So the first step would be to create the noise. Now, this chain of computation that you see is a very common technique used to generate procedural noise. Procedural as in it's not truly random. The same input always gives the same output, but it will serve our purposes for now. And it's very cryptic, very mysterious and esoteric, but two key things to note here is that the sine function creates the periodic appearance of the noise, creates a uniform wave-like pattern in the noise, so that it's not totally random, because sine itself is a periodic function. The next thing we're doing is we're using the fract function, which is also another built-in thing that you can find in the shader language, which will give us access to the floating point number of whatever we're calculating. And this means we can get sort of a nice continuous range of values going from 0 to nearly 1, 0.9999, which is great to get these noisy effects. And this multiplication by this mysterious large number just scales up the value to get a wide range of variation in the noise. All right, step 2, grab the input color of the thing that you're trying to shade. And here, what we're going to do is we're going to actually call a function called eval. And essentially, it's going to evaluate the incoming shader at the coordinate we're looking for. And when we call evaluate, the output is going to be the color of that texture or that input image at that coordinate. Cool. So this is the final part, and this is also the most interesting part. We have our noise. We have the color of the input. Now we got to mix them somehow. So we create a color using the noise factor and the noise variable. And this is going to be a grayscale noise because we're essentially putting all the RGB channels in the same way. And then finally, we're going to mix it by calling the mix function, which is a built-in function, again, in the language. And it allows us to mix two colors with a blend factor. And then finally, we're going to ensure that the final color that we output has the same alpha as the one that's coming in so that we don't mess up the transparency. And then we'll return the final color. But how do you actually use this in Compose? And that's where we get render effects. And you might be familiar with render effects because they're kind of used to create blur effects and things like that. But instead, here we will use a runtime shader effect. And this is only available API 33 onwards. So to create the runtime shader effect, take all our shader code, put it in the runtime shader, set up some of the uniforms, tell the shader what kind of size we're working with, and then finally we create the runtime shader. And here we pass in this string image, which exactly matches the uniform image that we saw in the shader program. And this is what essentially passes the entire render node of the composable into the shader as an image. Cool. Well, if you start applying some of these noisy techniques, you will see some erosion in the color, and it'll start looking a little dull. So one thing you could do is use a color filter and set the saturation and up that, and you can still get the noisiness, but now you have a bit brighter of a picture. All right, so here, we're just adjusting the intensity of the noise. And if you remember from just earlier, we had introduced a new uniform called intensity to tweak that. And here, we can kind of pass the value from the slider into the shader using the setFloatUniform function. And that string intensity has to match exactly the parameter name that we're using in the shader function. All right, so we have our work. What can we do with it? How can we export it? We can start taking screenshots of things, cropping them, but that really got very tedious, and I didn't want to deal with that anymore. So I was trying to look for a way to just capture the relevant composable and take a bitmap of it and share that out. Turns out there's a handy function called pixel copy that's available API 28 and above, and essentially allows you to create a bitmap from the thing you're interested in, and then use that bitmap, share it out, essentially copying the pixels over from the window. And the way that kind of works is you first create a bitmap with the dimensions that you know you want. You then define a rect, or you then define the position or the bounds of your composable in the window, and then pass in the bitmap and then listen for the result. And to kind of acquire the data needed to use all these, we can use the globally position modifier, which gives us the layout coordinates. And using layout coordinates, we can get the size of the composable to create our bitmap with. And then to figure out where in the window the composable lies, we can use the bounds in window function to get at the rect. So with that in tow, we can kind of add an extra button to our little control panel, and it would allow us to capture handy screenshots of what we're generating. So tweak a few things, hit that button, and then you can save the photo or share it or upload it. So putting this all together, you might end up with something like this. This kind of pulls in all the different interactive buttons and the shader controls and things like that. And it's just a lot of fun to play around with. And you learn a thing or two about graphics APIs, canvas, and shaders. So every run of your generative art program can birth a unique piece of art. Minor tweaks can yield dramatically different results. So if it can be altered, alter it, mess around with it, ruin it, it doesn't matter. Create bugs, have accidents, everything will turn out great. And creative coding is a bit of a cycle. So you might start out and you might think, these kind of look okay, but then all of a sudden, you'll do something by accident and you'll say, whoa, this is way better than what I had before. So a lot of this process is about picking things and choosing what you like and really going with your preferences and leaning into that, and then repeating and refining, seeing what works, what doesn't. And at the same time, you'll learn about a lot of interesting APIs. So don't stop at your first, second, or even 10th iteration. Keep refining, keep generating. For instance, the concentric circles one at the bottom was a happy accident. I did not mean to do that. I did that by accident. And I said, OK, whoa, this is trippy, so let's keep that. Honestly, I don't remember how that was done, so I couldn't tell you because I deleted that code immediately. That's another fun part of it. It's ephemeral. It's never going to happen again. Well, if you're stuck, ChatGPT is there for you, your BFF. So here, I really wanted to create a paint splatter effect, kind of like a Jackson Pollock situation. I knew kind of what I wanted in my head, but I just didn't know how to get started. So I was just like, hey, best friend, how do I do this? Can you help me out? And ChatGPT was like, of course I can. I'm a large language model, and there's a bunch of code for you. And this code wasn't nonsensical at all. It worked perfectly fine. In fact, I just had to do a few tweaks, and this is what I ended up with. So thank you, ChatGPT, for helping me in this journey. And it doesn't stop there. So it's not that you can just ask ChatGPT for like implementation ideas or like, how do I get started? You can also ask it to give you ideas, a kind of ironical departure from things like Midjourney where you tell it what to do. You ask it to tell you what to do. So here I was getting stuck. I was like, OK, I don't know. I want to do something fun, but I don't know what to do. So I'm like, well, can you give me some ideas around math concepts? What can we do there? And it's like, of course, here's 10 ideas. Pick any one you like. So I said, OK, well, the golden ratio idea sounds interesting. What can I do with that? So then I ask it, well, I'm using Jetpack Compose, Android, Kotlin. Please tell me what to do. And it did. And I cropped that out of it, but at the last line you'll see, let's take the golden spiral as an example, and make a composable out of it. So yeah, what follows was a bunch of code, and it was kind of cool. So yeah, if you're stuck or if you're just like, what the hell is this creative coding thing? ChatGPT is your best friend. And if you don't understand how to implement something, or if you're getting annoyed with, oh, well, this isn't just working out, like, where did that float go, or what am I adding +1 to something? Again, this will really help you out in that journey. Okay, so that's all I have for you guys. Thank you so much for your time and attention. I hope you enjoyed this exploration into the world of creative coding. Here is a QR code that has a link to the GitHub repository for the code. I will upload the slides later. There's also a bunch of resources in that README. Feel free to check it out. Feel free to code and create art. I think everyone here is not just a coder, but they're also an artist. And yeah, I would love to see the kind of stuff you guys create. And if you're really interested in creative coding in general, there's a huge community out there, huge community for generative art. Definitely take part in January 2024. Keep an eye out for that. Yeah, have fun. And have a great DrawingCon. Thank you so much.